All right, let's get started then. Um, I received a few questions, and I just want to make sure our understanding of linear regression is okay. All right, so let's say I was making a plot, and it looks something like this. Okay, let's say, all right, so let's say we are trying to predict I guess the cost. Yeah, we'll stick with this. Okay, cost of a flight. Okay, based on the mileage traveled. So this is just a review of last week's stuff. Okay, so let's say I said the cost is equal to okay, so I'm going to ask you a question. Now I know some of the students completely understand this topic, so if I could ask you guys to refrain from answering the question out loud. And then just maybe in your notes, just write down to yourself, what is the slope? Okay, and the interpretation of the slope. Okay, so the miles is measured in miles, okay, and the cost is measured in dollars. Okay, does this setup make sense? You guys did it for part of your lab. We were trying to relate the distance of a flight to how much it cost. Actually, 0.02 is vastly incorrect, but we'll just leave it. Okay, did you guys write something down? So, you know, every time I give you guys a moment to do something, I encourage you to do it at that time, because it allows you to test your own understanding and knowledge of the subject. Okay, what is my slope? 0.02, okay. And what is the interpretation of the slope here?
For every mile, price was
Okay, yeah. So for each additional mile, okay, we expect the cost to increase by $0.02. For each additional mile, we expect the cost of the flight to increase by $0.02. Is that okay? Does that make sense? All right. So this number was wildly wrong, but that's okay. Okay. And what is our intercept, and what is the interpretation of the intercept? And this would be our interpretation.
Flight of 0 mile cost.
Yeah, so this is, if there was a flight, if there were a flight, which there isn't, but if there were a flight of 0 miles, we expect the cost be $215. Yes.
So whenever there's a zero technically in front of the point, that would be before the decimal point. We figured out 0 miles, right? So a lot of the time in the homework in the lab, it
You
was
mean this?
0 miles, yeah. Because I look at the whole thing 0.02. Technically, we would
Okay,
look
so,
at the 0 before
I'm
and
in-
then 0 miles, right?
Yeah, I'm not sure if I understand your question, but it's more so as I think it's a style issue, where this is these two things are exactly the same thing.
I know they're the same.
Okay.
Yeah.
So
So-
what's your question?
I'll just ask you later.
Okay. Yes.
I have a question about intercept and interpretation.
Uh-huh.
When is it not appropriate to interpret it? 'Cause that
what-
doesn't make sense if it's 0 miles.
Yeah. That would
Is that what-
not that would be a time when the interpretation doesn't necessarily make sense. Okay, to have a flight of 0 miles, that's not a flight. That's staying put. Okay,
If the intercept was negative, how would you interpret that?
then it would be negative. I don't. That's okay. I'm trying to think of an example where it's negative and it makes sense. But I can't think of
Because
one.
I think one of the questions.
Yeah,
was-
sometimes you get a negative thing, and that's the thing, but it doesn't always make sense. Okay, so I mean, when you see something like 215, that's probably like maybe the .02. This is associated with the fuel cost, but the 215 is just everything else that goes into a flight, right? I mean, just the operating costs, just all of this other stuff, and then based on how far you're traveling, you got to tack on basically fuel surcharges and things like that. But, okay, I just want to make sure we're okay with chapter 4 stuff on regression and things of that nature. Yes.
Interception of slope and interception, the same?
I don't think there's such a thing as interception of slope.
You have it written down?
Interpretation.
Oh, I'm sorry,
Okay.
interpretation.
Yeah. Interpretation of the slope and interpretation of the intercept. Okay.
Is it the same thing?
No, this is the slope. I'm just asking, what does the slope mean in this context? Okay, I'm just asking, what does the slope mean? And that's the intercept. I'm asking, what does this intercept mean? Okay. Does that? No, you're still confused. Okay. I don't know. Or like, okay. The slope is this. Please translate into English, plain English. That's what I'm asking. Okay, and this is the intercept. And please translate this number, 215. What does that mean in English? That's all I'm asking.
Okay.
Okay? I hope we're okay. All right. And I have office hours every week. Okay, so a few students have come by, but
Where is your office? I was trying to
it's
find
in
it.
Math Sciences 8105J. Okay,
In locations from here.
you're gonna just
Because I'm
look
on
up
Fairfield
Math
here.
Sciences building. Okay,
Okay.
go to Google, type in UCLA Math Sciences, and then it'll show up. Okay, and if you once you figure out how to get to the building, it's too hard to explain how to get there from here. Okay, once you get there, you'll see some vending machines. Okay, and across from the vending machines, there's a glass doors. Go through those doors, and there's an elevator right there. Take the elevator up to the 8th floor, and my office is directly across from the elevator. And you open up 8105. It's a lounge. There might be other students there, and my office is in the corner of that lounge. Okay. I'm sorry, I couldn't hear you. Math Sciences 8105J, alright? All of this information is on the class website and syllabus. Yes. Okay, so please make sure you get chapter 4 down, and we will move on to chapter 5. and again, if anything is confusing, you know, post your questions on Facebook or send me an email or come to office hours, and I'll do my best to help you out. Okay. Last quarter, I would say there was a lot more activity in the Facebook group in terms of questions and topics being answered. So don't be shy. All right, chapter 5. This is all about probability. Okay. And before we get into probability, let me just ask you, what have you guys learned so far in this class?
A lot.
A lot. Yeah, thanks. Huh? Graphs? Okay, what kind of graphs?
Bar charts.
Okay, bar charts. And bar charts are used for what? Categorical data. Good. What other graphs? Histograms. And that's for numeric data. Good. What else is numeric data? What'd you say? Dot plots. And not yet. Okay. Box plots. Box plots. Okay. So you learned those. We learned how to describe data. Okay. How do you describe the center? Mean or median? How do we describe spread? Standard deviation. What else? IQR.
The range.
The range. Great. Z-scores don't describe spread. What are Z-scores?
Standard deviation.
The distance between like median something like that. From the mean. Number of standard deviations from the mean.
Number of standard deviations from the mean. The Z-score. Good job. All right. 10 points for Gryffindor. What else do we have? We got, last week, we created scatter plots, and scatter plots are for what?
The
Relationship between two numeric variables. Two numeric variables. And how do we describe the relationship between two numeric variables? Okay, we got strength and trend. Okay. And what? Shape. Okay. So if we've got a linear relationship between two numeric variables, how can we quantify this? How can we give it a number? The correlation coefficient. What symbol is that? R. R is for correlation coefficient. Good. All right. Well, I mean, I'm getting enough response that I feel like we're okay as a class as a whole. Okay. Some of you guys are being very quiet, and I hope it's just because you're shy. Okay. Or if you're having trouble keeping up, you know, don't be afraid to ask questions or approach me during office hours. Okay. And then we have linear regression, and with linear regression we talked about the slope and the intercept, and we also have to be able to understand what the slope means or its interpretation, and understand what the intercept means. Okay. Are we feeling okay with most of that stuff so far?
Yeah.
Okay. So today we're going to start talking about probability, and probability feels a little bit detached from the rest of the class, okay? Because we had all of this data stuff, and probability now, I mean, it feels like numbers, but it should feel like a little bit weird, and a lot of students don't like this chapter, and that's okay, all right? But it's an important concept, okay? We have to understand probability because in the future, we're going to use our understanding of probability to form the foundation of what we're doing. So probability tells us how likely something is to happen. Okay. How likely or unlikely something is to happen. And we're going to learn the rules of probability, which will allow us to figure out how likely or unlikely data is to appear. Okay, so far we learned how to describe data, and with our understanding of probability, how likely it is for certain data to appear or happen. And we're going to use this kind of logic to decide if a certain idea is feasible or not feasible. But we first have to understand this, okay? Because in the future, what we're going to do is we're going to have data here, and we're going to say maybe this data came from can be explained by this explanation. Okay, so we say, we gather data and we say, oh, maybe we can see this data because it's because of this explanation. But we've got to ask, how likely is this data to appear if this explanation is true? Okay, so and then we can answer whether it's likely or not. Maybe that's a little bit weird. Okay, but once we understand probability, if something is likely to happen, we can accept the assumptions, and if something is very unlikely to happen, we can say, maybe something is not true or not. Okay. So, for example, so there's this brain twister, right? And it's like you're going down the road, and you're at a fork at a road, and one person always tells you the truth, and one person always tells you a lie, right? Do you know this riddle? Okay, well anyway, it's like, if you can only ask them which one question about which road to take and things like that. But let's just say, let's say we were faced with something, and you meet a random person, and someone says, okay, so you can either say, maybe this person is going to tell me the truth, or maybe this person is telling me a lie, okay? But you're allowed to ask them a few questions, and you say, okay, can you tell me? And for whatever reason, you ask this terrible question, but the question is like, okay, who did you happen to see yesterday? Okay, and so let's say this person says, oh, I saw my classmate Sam. Okay. Does that, so based on that response, do you think this guy is telling the truth or telling a lie about any future answers? Well, I mean, you don't know, but if he says he saw his classmate Sam, there's no reason to believe this person is to be a liar, right? It's like, okay, that's entirely feasible. Sure, I'm going to give you the benefit of the doubt and assume you're telling me the truth. It doesn't prove that he's telling me the truth, but I'm just going to say I'm going to give you the benefit of the doubt. Because seeing a classmate Sam, not that unlikely, right? Okay, let's say, however, this person, you say, oh, can you just tell me, did you see, who did you run into yesterday? And this guy says, oh, I ran into Kobe Bryant. Okay. Do you think this person is likely to tell the truth or a lie? It sounds like, all right, this guy is making stuff up, okay? I mean, it is possible this guy ran into Kobe Bryant, okay? But it's unlikely, okay? And because it's unlikely, we're going to say, I'm not going to trust what this guy is saying. Does that make sense? We're going to use that concept in the future. But first we have to understand, is it likely or unlikely to see Kobe Bryant? Is it likely or unlikely to bump into your classmate Sam? okay? And so that's why we have to learn the rules of probability to help us understand what's likely and unlikely to happen, okay? And it's just a little bit unfortunate because the ideas behind probability feel abstract and kind of painful sometimes, okay? But it's a necessary part so we can understand what's likely and unlikely. Does that kind of make sense? All right, so there's a okay, so let me just pose you a very simple question. I say, if I've got a coin and I were to flip it, what's the probability this coin lands heads?
50%.
Okay. Okay, so some of you guys said 50%. Some of you guys said 50-50, okay? The way we're going to answer these questions is we're going to say the probability is 0.5, or we can say 50%, okay? So, we say, what is the probability that a coin lands on heads? And the answer is 0.5, okay? Or we say 50%. Now this is where it's very key that we can go from decimal to percentages instantly, okay? If we can't go from decimals to percentages very quickly, we're in trouble. Okay? We might write this. We might write the probability of heads equals 0.5. So anytime you write it like this, you're going to use the decimal form rather than percentage. But when we talk about it, speak of it, I'll say this, okay? So the highest probability that's possible for any so if I have some generic event, we'll say generic event A, okay, the highest probability it can possibly take on is what? 100%, which is equal to 1, okay? So this is the highest possible probability. And this means whatever A represents always happens, okay? So event A always happens. You can never have a probability greater than 1. So if you do some calculations and your probability ends up being 1.7, you made a mistake. You cannot have a probability bigger than 1. Okay? That's very important. If you guys screw this up on your quiz, I'm going to take off heavy points. On the other hand, if we have some other event, generic event B, the lowest possible probability is 0. And this means B never ever happens. Okay, and never happens isn't unlikely. Never happens means impossible. Okay? That's why it never happens. And again, you can't have a probability less than 0. Okay, sometimes we have something called simple events. Okay, simple events are experiments where every possible outcome is equally likely. Okay. So, if I flip a coin, what are the two possible outcomes? Heads or tails. Are they equally likely? Yes. So, flipping a coin is a simple event. Okay? Landing heads, simple event. If I draw a card from a deck, okay, shuffle deck, and I draw a card, how many possible outcomes are there? 52 in a standard deck. And is each one equally likely? Yes. Okay, so that would be a simple event. If I roll a die, what are the possible outcomes? It's the numbers 1 through 6. Okay, there's 6 possible outcomes, and each one is equally likely. Okay, what if I rolled 2 dice? Okay, how many possible outcomes are there? If we're talking about the total number. Okay, that's getting too complicated. There's 11 possible numbers. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? Is each one equally likely?
No.
No. No. Okay? The number 7 is much more likely than the number 2. And when you're rolling 2 dice. Okay? So that is not a simple event. Okay? So simple events. So examples of simple events. Okay, flip a coin, and we look at heads or tails. Okay, draw a card from a deck. Maybe roll a single die. Okay, we can get numbers 1 through 6. Or if we have a room full of people and I select one person at random, okay? Select a random person from a room. Okay, each person is equally likely. Okay. Non-simple event. Is let's say I rolled 2 dice. Okay, outcomes possible are 2, 3, 4, all the way up to the number 12, but these outcomes are not equally likely. Question?
I'm sorry to clarify this when you put it up there, but in say selecting a random person from a room, couldn't you argue that depending on how, if it's just a person standing at the front and you pick someone, that's not 100% random. I mean, if you had
So here the key is a random person. Okay.
Yeah, but so to select a random person, would you be able to just look at the group, or would you need to assign numbers and then?
Yeah, you'd need to assign numbers or do something, right? I can't just be like, boom, Okay, that's not random. Okay, this random is a truly random thing. Okay, and we'll talk about what it means to be truly random. Okay, most people's notion of random is not random, but when I write random, I really mean random. Okay, but we'll get back to that in a moment here. You're a little bit confused about what thing?
With the dice, with the two dice, if you do it, then like, isn't both of them have the equal chance of landing on the one? And so so you could get a 2, but why is it not equally likely?
Okay, there's so when you roll 2 dice, okay, how many ways can you roll the number 2?
One way.
There's only one possible way, alright? You gotta get a 1 on the first die and a 1 on the second die. Okay, let's imagine we got a red die and a blue die. You gotta get a 1 on the red die and a 1 on the blue die. Okay? How many ways are there to roll a 7? There's more. There's 6 ways. Okay, you can get a 1 on the red, a 6 on the blue, 2 on the red, 5 on the blue, 3 on the red, 4 on the blue, 4 on the red, 3 on the blue, 5 on the red, 2 on the blue, and 6 on the red and 1 on the blue. There's 6 different ways for you to get a 7. So those numbers aren't, different outcomes aren't equally likely. That's why when you play the game craps at the casino, okay, the game is essentially, you're trying to get your number to show up before the 7 shows up. And if you do, you win money. If you don't, the house takes your money. That's essentially, that's the game in a nutshell if you've ever played. Okay, that's the, okay, so whenever we're talking, for simple events and only simple events, okay, the probability of an event is equal to the number of outcomes in the event divided by total number of outcomes, total number of possible outcomes. Okay? So if I roll a die, a single die, what's the probability of getting an even number? Rolling an even number. Okay? So how many outcomes qualify for rolling an even number? 3. Okay? We can get 2, 4, or 6. Alright? And how many outcomes total are there? 6. 1, 2, 3, 4, 5, 6. So we've got 3 over 6, which is equal to 0.5. We have to be good with fractions too. Alright, are we okay with fractions?
Yeah.
Okay, you guys say yes, but I know that's not the truth for all of you. Alright. Are you guys familiar with a deck of cards? It's a standard 52 card deck. Okay, there's 52 cards. You can have ace, 2, 3, 4, 5, 6, jack, queen, or king. And you've got 4 suits You've got hearts, diamonds, clubs, and spades. Okay, 4 suits. So, I'm going to put a few just simple questions. What's the probability of drawing a diamond? So you draw one card from a standard 52 card deck. Draw one card. Okay, what's the probability of getting a diamond?
13. 25%.
Okay, what's the probability? Okay, don't shout these out. Just put these on your piece of paper, and then we can answer these. Okay, what's the probability of drawing a number between, we'll say less than 6? Okay, and that includes the ace. What is the probability of drawing a red face card? Okay, so those are your questions. See if you can answer them. Okay, face cards are Jack, Queen, King. The cards that have faces on them. Ace is not a face card. High value.
What's the second word?
Drawing a number less than 6, including the ace. So you can answer in fractions and or decimals. Doesn't matter, probably fractions, but decimals are fine. Okay, do we have answers for everything? You need another moment? One more moment? Okay, I can't give you any more moments. Okay. What is the answer to this one? What's the probability of drawing a diamond?
1.4.
Okay, so the answer is 0.25, and we got that. How many diamonds are there?
13.
There's 13. So number of outcomes in the event of, so diamond, 13 cards qualify for diamond. And how many events total, or how many possible outcomes? 52. So this simplifies to 1 out of 4, or 0.25. What's the probability of drawing a number less than 6, including the ace?
24.
Okay, so. Alright, what numbers are less than 6? Ace, 2, 3, 4, and 5 are less than 6. Okay, how many cards total are less than 6 then? 20, right? We've got 4 suits and ace through 5 in each of them. So we've got 20 out of 52. 20 divided by 52 is 0.3846. Okay, so we'll just write 0.385. Okay, and what about drawing a red face card? The probability is not 6, but 6 out of 52. Huh? How did I get 6? Okay, you got the Jack, Queen, King of hearts, and the Jack, Queen, King of diamonds. Those are the only red face cards. How did I get 20 here? Okay. So here, I'll write them all out. So here, 6 out of 52, let me just do this, okay. 0.115, okay?
How about heart?
Huh?
So we don't take heart as a red card?
Heart is a red card.
You said that you only
Card,
fake card,
Huh?
face cards that are red.
Oh.
Yeah.
So red face cards. Okay, so these are the 6 red face cards. We've got Jack, Queen, King of hearts, and the Jack, Queen, King of diamonds. Is that confusing?
Yes.
No. This is okay, right?
I didn't know.
You didn't know. Okay. So these ones are red, and these ones are black. And then here I've got ace, 2, 3, 4, and 5 of hearts, of diamonds, of clubs, and of spades. So there's 20 of them.
So we're supposed to know this stuff about cards?
Well, maybe not. I mean,
That's what I'm wondering, I don't know.
okay. I mean, if you're unfamiliar with a deck of cards, that's okay. I was just trying to think of most students are okay, I think, but I mean, always some students are always not familiar, and that's not your fault. It's just I'm just trying to think of a simple example of an example of a simple event that has more than like heads or tails or 1, 2, 3, 4, 5, 6 for rolling a die. So deck of cards, there's 52 and a few more things.
How can you see a simple event if there's more?
How can there be what? I'm sorry, your question again?
Is it a simple event or non-simple event? The things you just.
These are all simple events. These are all simple events because within, I guess, each outcome is equally likely.
Because
Okay.
there's a total of 52 outcomes.
Total of 52 cards, and when I draw one card, each card is equally likely
Out of 52.
out of 52, right? And so we just count how many qualify in one event, in one such event. Okay? Let's take a moment to talk about the idea of randomness. Okay. What does it mean to be random?
Unexpected.
Okay. All right. Yeah. So
Unpredictable.
there's we'll take on a simple definition. Okay. We'll say a random event has an outcome. All right. We'll say a random experiment has an outcome that is unpredictable. That does not mean we cannot understand it, okay? We will say, but we can still understand randomness. And what I mean by that is this. If I flip a coin, can you predict how it's going to land? No. You don't know if it's going to land heads or tails. Okay? So the outcome of an individual coin flip is unpredictable. However, we can understand something about it. If I were to flip a coin 100 times, how many heads should I get?
50.
50, okay? Will I necessarily get 50 heads? No, okay? If I flip a coin 100 times, maybe I'll get 47 heads. Maybe I'll get 58 heads, okay? Those are possible. Is it possible for me to get 90 heads out of 100 coin flips?
Yeah.
Technically, yes, but that would seem really weird, right? That would seem extremely strange. And we would say, there's something we understand about coin flips, okay? Any individual coin flip we can't predict, but we can say this outcome is unusual, okay? So we can say, if I flip a coin 100 times, I shouldn't get 90 heads. If that happens, something's probably wrong with my coin or the way I'm flipping the coin. Okay, so we'll say that. So we cannot predict you still cannot predict how many coin flips predict how many coin flips will land on heads if I flip it 100 times. We can say so coin flips are random events, and we can't predict any single outcome, but there is something we can understand about it. Is that okay? We have, so in real life there are random events. Well, I guess it depends what your philosophy you have about life. We'll say, in real life, we can consider some events to be truly random. Okay, so coin flips. Okay, or if I put slips of paper in a hat and I mix it up and draw a piece of paper out of the hat, that can be considered random. Okay, so those can be considered random. And sometimes other events can be random, like selecting a random person from this class, okay? Or sometimes we want to do a random event, but how can we do that? How can we select a random person set something up so every single person has an equal chance of being selected.
Draw names out of a hat?
Yeah, so I could have every single person put their name on a slip of paper, put it into a hat, and draw a name out, right? So method 1. Okay. Put each name on a separate paper or separate slip of paper. Draw it from a hat. We can do that, but that can be tedious if we have like 200 students in the class or something like that, right? So, so another way is I take the class roster, or take a list of everyone in the class. Number it from, we'll say 1 to, let's say there's 62 of you, and then randomly select a number from 1 to 62. Does that sound good? Nobody's going to ask me how I randomly select a number?
Yeah, that's what it is.
How do you randomly
How do you randomly select? Thank you. It's just the question I was asking. So how do we randomly select a number from 1 to 62?
Draw from a hat.
The numbers 1 through 62 on a piece of paper and draw from a hat. No, that's silly. Okay. Well, there's a few things we can do. All right. No, I'm not going to close my eyes and go, because as a human, I am terrible at being random, okay? You guys might not realize this, but if I asked you guys, think of a number, a random number in your head, between 1 and 10, okay? Don't say anything. Okay, you guys are more likely to pick the numbers 3 and 7, and less likely to pick the numbers 2 or 9. I don't know.
4.
Huh?
Or 4.
Or 4, whatever, okay? So some numbers are more likely and others are less likely, okay? And 10 probably won't be selected either, but maybe some of you guys selected 10, okay? So, randomly select a number from 1 to 62. So we can do this using random tables or a computer, okay? This part, randomly select a number, okay? This can be done with a computer or a table. Table or a computer. Okay. In the back of your book, I think on page A1, there is a list of random numbers. Random digits is what it's called.
Wait, but how does like the computer take a random number?
Random digits. How does a computer? It's not truly random, but it's what we call pseudo-random. They're pretty good at being random. It uses a computer program. You can look it up. If you're into computer science, you can look up random number generators. Go on Wikipedia, look up random number generators. The Mersenne Twister. This is a good random number generator. Okay, don't bother. Okay, only for those who are interested, not for the faint of heart. Okay, and you probably should have a background in computer science if you want to get anywhere with that. But we use there's computer programs that will generate sequences of numbers that are, for all intents and purposes, random, can be considered random. Okay, but anyway, random digits, we can simulate the digits 0 to 9, okay? Each digit 0 to 9 is equally like alright? So it's basically you can in the back of your book on page A1, I believe, is a random number table. Okay, page A1. And just imagine the way this, okay, just imagine someone put the digits 0 through 9 on separate sheets of paper, put them into a hat. Put 0 to 9 on pieces of paper into a hat. Okay, and then this person draws out a number, writes it down, puts it back in the hat, mixes it up, draws out another number, writes it down, puts it back in the hat, mixes it up, and does this for a very long time. Okay? Draws a number or a digit, records it, puts it back, and mixes it up again. Mixes up the hat. Repeat. Okay, does that make sense? And so now we're getting a whole bunch of random digits, 0 through 9. Each one, so is it possible to get the same number twice in a row?
Yeah.
Yeah, sure is, okay? A 0, put it back, I draw out another 0. No big deal. Okay? So using this, I can randomly select a number from 1 to 62. How do I do this? Okay, so let's, so somebody has gone through and taken pieces of paper out of the hat and wrote down the number. And the first number they got was a 2, the next number they got was a 1, and then they got a 0, and then they got a 3, and then a 3. I'm just looking at table A1, and it keeps going. 3, 2, 5, 2, 2. One 9 3 0 5. Okay. If I only had 10 students in my class, this would be easy, right? If I want to pick the, when I do this, the first student I pick will be student number 2. And if I get this, the next student I pick will be student number 1. And then if I get this, this will be the what? 10th student, okay, student number 10. And then I draw student number 3, and then here, I can't draw student number 3 again, so I keep going, just like that. Does that make sense, or that doesn't make sense?
Kind
Why
of
would that be a
confusing.
10th student?
Huh?
Why would that be a 10th student?
But the 0, why would that, oh, because you can't go to learning.
So, okay, so let's say I have 10 students. Okay, I've got Adam, Bob, so on and so forth. And I just number them. Student number 1, student number 2, 3, 4, 5, 6, 7, 8, 9. And then instead of writing 10, I'm going to give the last one student 0. Okay? And now, I'm just going to, when I drew numbers out of the hat, the first number I got was 2. So I select Bob. The next number I draw was 1. So I select Adam. And then I draw 0. So I select student number 10, okay, or student 0. Does that make sense? Okay. But now I don't have 10 students. Okay? How many students do I have? I got 62 students. Okay? 62 students. So I still, you know, maybe I have Adam and Bob again. And I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to student 62. So how can I draw students from 1 through 62? Yeah.
Could you use the first two digits, like 21, 03, 33?
Exactly. That's what I'm going to do. So I'm going to group these two together, and I'm going to draw student 21. And then I'm going to group these two, and I'm going to draw Carl. Okay, so technically all of these are now 01, 02, all the way up 10, 11, 12, all the way up to 62. Does that work for you guys? So the next student I draw is student 33, then 25, then 22, 19, 30. Okay, so let's say my next four numbers are, so what's the next student I draw?
54.
Student 54, and then?
87.
87. Okay, but do I have student 87?
No.
No, so what do I do with this?
Take it out.
I just ignore it. Okay, I don't have student 87. Okay, and I keep going. Maybe I get 63. Can I draw that?
No.
No, I ignore this one. Okay. What if I have 54 here? Okay, well I've already selected student 54. Okay, so I have to ignore it. Okay, but it depends on the situation. Okay, I mean if we're talking about if it's allowed for someone to be selected twice, then fine. But if it's not allowed, then we have to ignore it. Okay, so it depends. Okay, keep if you allow repeats. Ignore if repeats are not allowed. Okay, so we can use random digits, and computers are good at simulating random digits to make to do things that we want to do randomly. I'm sorry?
Did you make up the 62 for the
I made up the 62.
Okay.
But that's about how many students we have in
Okay.
And
Okay.
you chose to keep them in two.
Because one digit is not enough, right?
If you had 300 students, would you do then?
Yeah, if I had 300 students, how many digits would I need?
3.
I would need 3. And I would be throwing away a whole lot of students, a whole lot of numbers, right? Anything over 301 or higher, I'd have to ignore. Okay, so I'd be throwing away quite a bit, but that's the only way I can,
Be random.
for it to be random, okay? So we have theoretic probabilities. Okay, and these are found using the rules of using math rules. Okay. Okay, so. What's the probability that a coin lands heads? Okay. The way we got 50% was we used the math rule that said there's one side of the coin that lands heads out of a total of 2 sides, so we get 0.5. Does that make sense?
Yeah.
Alright. What if you've never seen a coin before, and you have no concept of a coin flip? Okay, you're an alien visitor, and you've never seen a coin flip, and so you want to know, you know, what's the probability that a coin lands heads, but you've never seen a coin flip, you don't even understand how a coin works, okay? How can you figure this out? Yeah?
Well, I think they would understand there's only 2 sides.
Okay, so let's say this is like so weird, okay? This, I don't know. What we're going to do is, on the other hand, let's say, okay, so this is really easy to figure out. Probability of heads, there's 2 sides, one of them is heads, so 1 out of 2. On the other hand, some things are a little bit more complicated, okay? And what we can use to answer, figure out the probability is we can do the empirical probability, okay? And this is found using trials, okay? So based on experiments, based on trials of experiments. Okay? And this would involve flipping a coin a whole bunch of times, counting how many times it landed heads, and using that as an approximation of the real probability. Okay, so let's say we flip a coin 1,000 times. Okay, let's say it lands heads 513 times. So my empirical probability is equal to what? 513 out of 1,000, and this is equal to 0.513. And so, based on the 1,000 coin flips that I've done, so again, I don't know how a coin works, okay? And but after flipping it 1,000 times, it landed heads 513 times. So at this point in time, if I were to flip it, if somebody says, if I ask you the question, what do you think would happen if I flipped the coin another 1,000 times? What's your best answer? It would probably land heads 513 times, okay? Because this is all I've seen of coin flips thus far. Does that make sense? Okay? And so sometimes we can answer questions using our math rules. In this case, it's very easy. And other times, we don't have a set of math rules to answer questions like this, right? What if I ask you, what's the, if I select a random person in the United States, what's the probability that this person is of Latin American descent? Okay? So I'm asking, if I pick a random person in the United States and I ask what's the probability that this person is of Latin American descent? Okay? Well, we don't have math rules to answer this. Okay? We can't be like, oh, well, based on anthropological evidence of migration patterns and things like that, we don't have math ways to figure this out. So the best we can do is empirical probability. We take a census, or we take random samples of people, and we ask them survey questions, and we say, please check your ethnicity, or give us your ethnic backgrounds, or things like that. And based on that evidence there, then we come up with an empirical probability. Okay, so sometimes this is the best we can do. And this number may or may not be truly close to the real probability or not. Okay? But, okay, so sometimes we use empirical probabilities. Okay, especially when the math rules get too complicated. Alright, the rest of this class we're going to focus on the rules for finding the theoretic probabilities for more complicated situations. Okay, so if I roll a die, what is the probability of rolling the number, rolling a 2?
1 out of 6.
1 out of 6, right? 6 sides. This answer, so let me just write probability of 2 1 out of 6. Okay, good job. Alright, so then what's the probability of not getting a 2? So this we write probability of not 2. This is equal to what? 5 out of 6. Now how do we get 5 out of 6? Okay, so this can be found using the what we call the not rule, or it's called the complement rule, is we do 1 minus the probability of getting a 2. So I do 1 minus 1 out of 6. And this is equal to 5 out of 6. Okay, can we see that? So we have to understand fractions to know that 1 minus 1/6 is equal to 5/6. Okay. Yeah, this is so this is called the complement. Okay, complement here is spelled with an E. Okay, it's not a compliment, which is a nice thing you say to someone, but a complement, which is something that's used to complete the picture. Okay, because between rolling a 2 and not rolling a 2, that covers every single possible outcome of rolling the die, right? When you roll a die, you're either going to get the 2 or you're not going to get the 2. There's nothing else possible. So that completes the picture, the complement. Alright? So if I say I'm going to pick a random person, pick a random person. Let's say the probability that this person is left-handed is equal to 0.15. What is the probability